this tutorial, we're going to study complex numbers and look at the Moivre's theorem. But before that, let's recap a few things we did in the previous assignment. Most importantly, inverses and complex conjugates. As I draw my usual diagram, so here's the complex number z. Let's consider the additive inverse first, which is just none other than minus z. So z plus minus z equals 0. In polars, minus of r comma theta p is equal to r and theta plus pi, because the negative corresponds to rotating by pi by 180 degrees into the negative part. There's minus z. So in the more familiar format of minus x plus iy, this is just minus x minus iy. For the multiplicative inverse, also known as z inverse, well, what do I need? I need z times z inverse is equal to z inverse times z is equal to 1. So in particular, we need z is non-zero. And if z is equal to r comma theta p, then z inverse is equal to 1 over r minus theta p. The size, let's say this is 1. The size of z inverse, remember that z is, let's say it's this big, then the size of z inverse is 1 over the size of z. And the angle, remember that when I multiply z with z inverse, the angle must add up to 0 along the real line. It must be there. Let me make it a different color. What about the complex conjugate? That's z bar, sometimes also written z star. This is a reflection along the real axis. So this sends z over to z bar over here. And you can see that actually it's got to be on the same angle as z inverse. Let me just draw it here. So in polars, z bar is equal to r comma minus theta p. The angle just of z, if this is theta, we get to minus theta. And it's also equal to x minus iy in Cartesian coordinates. Now, let's look at real and imaginary parts. These are just the x and y coordinates. So if I have this complex number z, which equals x plus iy, we can see that the real part of z is just x, and that's equal to z plus z bar over 2. Let me just remind you that z bar was this reflection along the real axis So that z plus z bar is there, and that's equal to 2 times the real part of z. Similarly, the imaginary part of z is y, and that's z minus z bar, not divided by 2, but divided by 2i. So if I subtract off z bar from z, this reaches this point, which is 2iy. And I have to divide by 2i to get to the value of the imaginary part. If you want to check, let's just check. Let me check the first one. I'll leave it up to you to check the second. X plus iy plus x minus iy all over 2 is equal to 2x over 2, which is equal to x. So as promised, let's state de Moivre's theorem, or a version of it. This says that r comma theta to the n in polars is equal to r to the n theta in polars. And this is just straight from the definition of multiplication of complex numbers. You see, the size takes the power, multiplies it by itself, and the angle adds itself n times. If z, which equals r comma theta p, is non-zero, then this thing also holds for n a negative integer. In the case n equals -1, we get that r comma theta inverse, which is just z inverse, is what we wrote earlier. It's 1 over r, and the angle is minus theta. So the consequences, as we covered in class, let's do 2 examples. They're mainly trigonometric. So let's take r equals 1 and n equals 2. So this says that 1 comma theta squared is equal to 1 comma 2 theta. And on the one hand, this is equal to cos 2 theta plus I sine 2 theta. Remember, this is the Cartesian form of this polar form. The picture here is you take something on the unit circle, take an angle, theta, there's 2 theta. Draw a bit better. And that we can relate the causes and the sines of these 2 complex numbers, which are the real and imaginary parts, and we can find some relationships. This is cos theta plus I sine theta, all squared, and that's equal to cos squared plus I 2 sine theta cos theta plus I sine theta squared, and I squared is -1. And so we get that this is cos squared theta minus sine squared theta plus I 2 sine theta cos theta. Equating real and imaginary parts, we get identifications of cos theta in terms of cos squared minus sine squared, and sine 2 theta in terms of 2 sine theta cos theta. A slight slip of the tongue there. It should be cos 2 theta is equal to cos squared theta minus sine squared theta, and sine 2 theta is equal to 2 sine theta cos theta. As an exercise, so just to check if you're watching these videos, try for two complex numbers with different angles, but both sides 1, obtain some trig formulas using these. So in the case r equals 1 still, and n equals 3, we get that exactly the same process. The Moivre's theorem says that the complex number multiplied by itself 3 times is the same size, but with 3 times the angle. The picture is, so there's theta, there's size 1, and along the circle, there's 2 theta, still can't draw it, and then there's 3 theta. So on the one hand, this is cos 3 theta plus I sine 3 theta, and this is equal to cos theta plus I sine theta all cubed, which by the binomial theorem using Pascal's triangle, okay, this is cos cubed plus 3 cos squared times I sine plus 3 cos times I sine all squared plus I sine cubed. And this is equal to, if I equate the real and imaginary parts, this gives me a minus I squared, and this gives me a minus I. So this is the real part, and there's the imaginary part. The minus comes from the I squared. So again, equating real and imaginary parts, we get that this bit is this bit, and that bit is that bit. If I using sine squared plus cos squared is always 1, we can convert sine squared or cos squared, and we obtain that cos 3 theta, which is cos cubed theta minus 3 cos sine squared. This bit is equal to 1 minus cos squared. And so this overall is 4, so which is 1 plus 3 cos cubed theta minus 3 cos theta. And exactly the same argument, but applied to sine 3 theta this time, which is the green one, you obtain that this is 3 sine theta minus 4 sine cubed theta.